Hello YouTube, hello everyone. We come back to electrostatic revision. It's all about interaction, different particles, charge extended bodies or objects with each other. Where in this case, we're not talking about electrodynamics, so we don't consider any particles in its motion. So that's why they might experience different force, and as a result they might have acceleration, but we're not talking about electrodynamics. All right, hope you got it. So today we will consider interaction of two charged spheres, and of course we'll be considering the general force of interaction. Hope you got a clue from problem 1. That was about particles interaction. Now we go to extended bodies. And you can see here, electrostatic interaction versus like general interaction, because obviously two charged spheres, if they have mass, if it's not negligible, they can interact in a way, not only electrostatic way, right? They can interact through the gravity force, gravitational interaction. But I hope you got the clue about particles interaction in the previous problem, that this force is pretty negligible. Alright, so those hints you can use here in problem 2. If you haven't watched problem 1 about particles interaction, I encourage you to watch, because you will have the basic principles and basic concept of how interaction goes, alright, in terms of electrostatic force, in terms of Coulomb force. Alright, too many words, let's get back to the problem itself. And as always, grab your pen, grab your notes, try to do by your own. So here's you have interaction force that need to be calculated between two spheres. Okay, they're not balls, they're spheres, and each of mass 1 grams. So they both made of the same material, copper, and they're separated by a distance 1 meter. And the total electronic charge in each sphere is different from the total charge of the nucleus, okay, by 1%. All right. As you understand, the total electronic charge can be as greater as well as lower by 1%. Okay, it's just the difference. Of course, if it's greater, you'll have a negative total charge on each sphere. But if it's lower, you have the positive as a net charge. Okay, so bear this in mind, and let's draw up two spheres. First of all, I just want you to think more generally. So if you have two spheres separated by a distance 1 meter, okay, so we assume that they're separated by a distance, and this distance is measured between the centers. All right, so that's going to be an idea. So 1 meter here. All right, so that's the distance of interaction. So maybe it's better to put r as the distance. Okay, so that two centers. As you understand, because you have copper is a conductor, and as is in any conductor, even in the case of electrostatic, you might have free carriers, right? We're not talking about the current, but anyway, if there are free carriers, they have ability to move, even if you consider electrostatics, right? So what I'm talking about possible extension, because as you understand, if they, for example, there is electronic charge is greater than the total charge of the nucleus, basically the proton charge. If it's greater, there is excess of electronic gas, right? And what might happen? So actually, electronic gas are freely to move, and that means due to the fact of repelling, you'll have most of the case electronic charge mostly on the outer parts of the shells, right, of the spheres. And that means it's slightly changed distance of interaction. Okay, so that's thoughts you might use in maybe some prospective problems. I'm thinking about problem 3, which is going to be about spheres and the effect what I described right now. the case that electronic gas can freely move along the surface, and due to the fact of repelling, it actually slightly shifted, and that's why hence increasing the distance of interaction. All right, but let's set up this extension for the next problem. So today we have a pretty simple picture, so we just get rid of that, and we assume that the charge is is distributed uniformly. Okay, so that's why we can think about effective distance of 1 meter between the centers. And of course, because sphere is the best example of when we can apply Coulomb's law, and force of interaction between those spheres actually can be calculated in a normal way. So we can say that electrostatic force, attraction or repelling, doesn't matter, can be calculated through this standard formula, right? So I will set up the effective charge as Q effective, and obviously it should be squared because both spheres will have this effective charge according to the problem. However, we haven't calculated this yet, but the general formula is already done. Okay, so that's electrostatic force of interaction, or Coulomb force, where K is simply 1/4 pi epsilon 0, and value for K is around 9 times 10 to the power of 9. Okay, so let's do the next step. The next step is, of course, we neglect with gravitational force. Can you imagine that in problem 1 we discovered that this ratio is quite big? I mean, electrostatic force is much greater than the gravitational one. So there was the order about 10 to the power of 42 for the ratio of electrostatic force to the gravity force, to the gravity. So that means we can definitely neglect it. That was, by the way, it was for 2 electrons interacting. Here, there is much more charges concentrated on the sphere, all right? So that's why, on top of that, you may say that this ratio is going to be much greater. So obviously we neglect with gravity force, so gravity force is much less than electrostatic one, and simply interaction force is represented purely by electrostatic force. Okay, so what's the next step? So the next step is pretty obvious. In order to calculate effective charge on each sphere, we need to be careful about that. The total electronic charge in each is different from the total charge of the nucleus by 1%. So let's have a look at the greater picture, how to calculate nuclear charge. So nuclear charge, it can be calculated through basically the total number of atoms times the elementary charge of the electron, number of atoms, and times, so that's basically for each electron or for each proton, right, which inside the nucleus. So we just have a look at the Mendeleev table for this particular element, for copper. Okay, so, and you can see that there are 29, okay, 29 electrons or protons inside this particular element. So basically this is what is called atomic number of electrons. Okay, so if it's 29, obviously for the total charge of the nucleus represented by 29 protons inside, we need to multiply by 29. All right, so I hope you got it, and we move next. So what's the next step? The next step is to calculate number of atoms, because we have no idea right now. So what we have the mass. So that's why actually number of atoms can be calculated through number of moles, right? Number of moles, I used nu, but you can use this one, this symbol, and times an Avogadro. okay? So which is represented by 602 times 10 to the power 23. Okay, so number of moles, basically how many moles on each sphere, how many moles? We can calculate this parameter through the mass over the molar mass. Hopefully we know molar mass for copper, and again, just have reference to Mendeleev table. It's 63, so just put right here. So for the copper, so we have 1 grams and over molar mass, which is 63.545, yeah, 546. So we can round up, but that's what we will have. So gram per moles. Okay, so we have that, we have molar mass, and we can calculate the quantity. Okay, so now we can figure out number of atoms. So, and hence we can calculate nuclear charge. Let's combine everything at once. So nuclear charge, sorry for that, nuclear charge. We can do the following. So 1.6 times 10 to the negative 19, that's electronic, that's the charge of 1 electron. So we multiply by number of atoms, which is simply 1 gram out of 63 and 546, okay? And next we multiply by Na, which is N of Avogadro. So that's why we'll get here 602 times 10 to the power 23. Okay, so that's how much we will get here. And we multiply everything by 29 as the final step here. All right, we took into account, I hope, all the factors. That's going to be the total nuclear charge. Okay, now we have, according to the statement, that the total electronic charge is different of the total charge of the nucleus by 1%. So that's why each charge on the sphere, which is Q effective, is going to be equal total nuclear charge that we've calculated here. So nuclear charge minus total electronic charge. So total electronic charge. That's going to be the effective charge. So in which way we can calculate? It differs by 1%. So we're taking from the nuclear charge 1 over 100. So we're taking from that 100, basically hundreds, only 100 parts of that. So we can calculate the total amount of charge that sits on each sphere. So we just apply that, and that's going to be equal 1/100 out of what we're going to calculate here. That means, so if you take calculator, I hope you do or already done. So it's going to be around 4.3 times 10 squared coulombs. Okay, we've got effective charge, and we can square this up. Divided by 1 meter and times k, which is the constant. Okay, so in this case we can figure out the final result for the force of interaction. So force of interaction is going to be equal 9 times 10 to the power 9, so times what we've calculated here. We've calculated 4.3 squared and 10 to the power 4 hence over 1 meter squared. Okay, that's going to be, I hope, the final result, and the result for the force of interaction is going to be equal 1.74 times 10 to the power 15 in newtons. So that's going to be the final answer to the problem. So this is the force of interaction. Alright, so we've done that. I showed also an extension for this problem, and I hope in the next stage I'll demonstrate maybe more qualitative things about interaction of two spheres, take into account that charges can be freely moved and relocated, and hence they will change definitely the force of interaction. Alright, we'll see that. That was Daniel Dallas. Thanks for watching and see you in the next episode.